to my talk. This is a reverse engineering conference, but I think it's time to talk about the topic which is dealing with the protection part. And the name of my topic is hardening, which relates to the number of protection schemes against reverse code engineering with multi-threaded packing nets. A very long title. Maybe you remember my introductory words yesterday in the discussion when I said every protection is crap. So this might be a crappy talk, I don't know, you have to decide. So, just an overview of my talk. After the introduction, I will give a short overview about Petri nets. I'm not sure if everybody knows what Petri nets are, so it's better to talk about some basics. I give a brief example on how to use Petri nets. Later on, we jump to protection by obscurity and obfuscation, because both topics belong to the hardening part. Later on, I show a live example how to protect with Petri nets. Later on, a discussion, and I will show some results. So, what are known problems? Known problems are, for example, software piracy. You know all cracks and key gangs. As well, plagiarism is a very huge problem. One example of plagiarism is to rip the code out of the application and use it for your own application. And algorithm theft is always of interest. As well, I don't know if somebody is coding viruses out here, but if you want to encrypt and want to hide viruses, it's always of interest for you that the virus analyst is not able to understand what you are coding about. And of course, one more problem is reverse code engineering. This includes disassembly, static and dynamic disassembly, decompilation, code transformation, code flow reconstruction, and of course, analysis and understanding. Because if people want to understand the code, and we want to prevent it. So, what could be one method of resolution? One method of resolution is to decrease the code understanding. If you disassemble a code and you're not able to understand it, it takes some time. Maybe you play days, maybe you play weeks with this, but someday you are anymore interested maybe in cracking the protection. So one way is hardening through obscurity. It makes the code very obscure. The person who analyzes the disassembly do not understand what's going on. It's one goal to play with the cracker. Another way is to obfuscate the code. I'm sure that everybody knows what obfuscation is, and Griffiths had taught us his talk. But another way, you can harden your code through complexity. You can make it just more complex. Increase the size. You know, if you try to reverse code engineer an assembly application, it's partly very easy to understand. But if you ever have to try to trace P-code application by Visual Basic, it's horrible. Because you have tons of chords, you do not understand what's going on. You really have to extract the useful information from the useless information. Visual Basic is a good example for very much useless information in the code. You could be able to manipulate the code flow graph and the information flow graph. As well, it's a typical method for obfuscating applications. And one more way would be to use Petri nets. If you look at the right side, it's just a simple C application. And, well, do we have some very good C developer out here? You can tell me what this application is doing? Okay, so on your first view, the simple C application is not readable. It will take maybe hours to understand it. So the obfuscator has done a good job. So just an overview about Petri nets. Well, a Petri net is a method to represent processes in an abstracted way. So what are processes? We can divide processes in uninteresting and interesting processes just for this talk. Processes are everything. You can talk about processes in factory workflows, business flows, communication flows, which means you can describe protocols with processes, device controls, handicraft manuals, and one good example are biological pathways. That's very important in the field of bioinformatics. Interesting processes for us are software development processes, software algorithms, and of course, registration number machines. So we can put nearly everything into kind of a process. And one very good thing about Petri nets are the simple graphs. You can sketch them on paper. It's very easy to deal with that. And they have one advantage: you can run them multi-threaded. So what types of Petri nets do we have? It's just a small abstraction. There are discrete Petri nets, autonomous Petri nets, stochastic Petri nets, hybrid Petri nets, and so on. There are whole research groups just dealing with this topic, how to analyze, how to deal with Petri nets. For this talk, we keep very simple. That's the basic of Petri nets, just simple graphs to make it easier to understand. But you see, you can make it very complicated if you like. So just a formal definition, because it's necessary to understand how Petri net is based. Petri net is a 6 tuple of ST, FK, W, and 0. So what does it mean? We have a non-empty set of locations. The term for these locations is places. Then we have a non-empty set of transitions. Okay, the transitions. And we have a non-empty set of edges, arcs. Okay, if you know something about graphs, it's very simple. You have nodes, you have edges, and you have a kind of transitions. As well, you can add a special capacity of places for tokens. You can put in these nodes of the graph several items, call them an impeachment token. And like for other graphs, you are able to, weight the edges, to influence the model of the network. And finally, we need a starting model. Somewhere we need to start when we need to simulate something. So somewhere has to be marker. For those who are the friends of math, you can look at the right side, it's a right definition of it. But very simplified, you just have 3 objects. We have places, transitions, and tokens. That's it. Very easy to play with until now. It's true that no object can belong to both sets if you look at the mathematical definition. And between places and arcs, there might be a relation. Of course, if you draw a graph on paper, you can connect the nodes, but you don't have to. There's no need to connect nodes, right? What else? It can simulate something. You don't know what it's simulating at the moment, you can simulate something. And so the Petri net is kind of a runnable process graph. So on the top left, you see a very simple Petri net. On the left side, you see a plate which contains a token. It's just filled with some kind of information. In the middle, there's a transition. And if you want to move the object, the token, from the left place to the right place, it has to go over the transition. The transition decides when and if the token can move from place 1 to place 2. If you look at the upper small graph, you see the token at the left side. After the transition is fired, you can see that the token is in the right side. So the transition has moved the token from one place to another one. So it's important to understand that within Petri net, you're not only able to fire one transition at one time. And if so, a transition removes as many tokens as the weight of the arcs defines. So you have the freedom to define over the weights of the arcs how the model is behaving. And the places after the transition should receive the tokens. But the places before the transition need to have enough tokens to fulfill the definition of the transition. And for sure, you have to need enough place behind the transition to fill this up. If it is overfilled, you're not able to put any more tokens in the place. Okay, the transition which is able to fire, to do a transmission, is called activated. But this does not mean that it's really fired. It depends on the model. And next, Petri net containing no activated transitions is just called a dead Petri net. So it might happen very much at all. So Petri nets might save lives. One good example is the 5 Chinese sages problem. And here we have 5 Chinese sages are sitting at a circle table and have dinner. Between of each 2 sages is only 1 stick. But for eating each of them needs 2 sticks in a moment. Obviously, if all sages take sticks from the left side and waiting sticks from the right side, they all die through starvation. Sounds to be a very complicated problem. It's a funny problem. So how can we solve this by Petri net? Well, the Petri net for this problem looks like this. We have in this network places P1 to P5, which introduce our sticks, which are laying on the table. And all sticks are on the table at the first moment. And each place, for sure, has a marker inside. Because we want to move the sticks through our network, or through the table, however. The transitions T and E introduce different states the sages can have. So T stands that the sage is thinking, and E is that the sage is eating. And to pass from the state M to the state E, from the startup marker to the eating marker, both sticks have to be at the same at the table at the same moment. I will tell you if this problem is solvable about this Petri net, so you have some fun maybe to try it out yourself. But it might be that it's solvable. It sounds very complicated, the graph is looking very simplified, but I don't tell you, maybe you can play with it. Think about the problem. It's a nice brain tutor. However, we might have some conflicts within our Petri nets. It might happen that two transitions need the same token. And both transitions are activated, but only one can fire. This is not an error in the Petri net, but you have to take care how to model the Petri net. You have to decide which transition, for example, has the right to take tokens or not. If you have two different transitions, maybe, who are fighting for one token to get a token, you have to design in your model how this could work. There are several other conflicts, post-conflicts, confusion conflicts. We don't want to go into the deep of this, but it shows that Petri nets maybe look simple, but they can be very hard, especially if you want to model them. So, next, protection by obscurity and obfuscation. Given a program P and an obfuscated program who have several definitions, these have been defined by Christian Kohlberg. He's doing very much in the field of watermarking, software obscurity, complexity, more in the field of Java development, but it's very funny to play with this tool. He has developed a tool called Sandmark, where you can very easily try to adopt different watermarking techniques, code obfuscation examples, and so on. And if an obfuscated program has the same observable behavior as a normal program, this means that the transformations are semantics preserving. Of course, if you try to obfuscate the software has to do the same thing after obfuscation than before. If you look outside, there are several obfuscators. It's not always the same. Sometimes they obfuscate things, the code is different after obfuscation. So not very good development. The obscurity of the obfuscated application is maximized. So the understanding of reverse engineering is definitely more time-consuming for an obfuscated software than for the normal software. And that's what we want to do. We want to make problems for the analyst. The resilience of each transformation is maximized. This means it is very difficult to build an automated tool which can remove the obfuscation. It would be easy if you have an obfuscated code, source code, and you just run a tool over it and everything is fine. I cannot remember any real good tool which is able to do this. It's a big problem. So it's always a problem for the person who's analyzing this. You always sit in front of the code, you try to do this manually, you're moving lines, you're trying to fix the code just to get the good code back. The stealth of each transformation is maximized. This means that the statistical properties of the obfuscated source code and of the normal source code are equal or similar. And for sure, the cost which is incurred by the transformation is minimized. For sure, we want to reduce execution time and space during the obfuscation process. If you just confine to the basics of this obscurity and obfuscation part, code obfuscation is very similar to code optimization. There are just maybe two differences. With obfuscation, you are maximizing obscurity while you are minimizing the execution time. If you do optimization, you just reduce to minimizing execution time. Well, that's not always true. If you see several compilers, well, they do strange things in compiling the code. And I'm not always sure that optimization flags makes it, makes the application faster. So this is one example how to protect this feature net. At the top we give in our registration number with four simple numbers: P1, P0 to P3, and we mark the network, the feature net, at its initial state. We just give in an input and let the network run. And for our model, we define that if transition T2 is executed, T2 is marked with a circle, the red circle, then the feature net problem is solved. So starting this network could lead to several ways, but this feature is just one way. And it's very important to see that we have at the place P7 the pre-marker set. So our model is filled with some information before we run. Normally the cracker should not see the layer below the red line. I don't want to talk about how to protect this layer, but if you just put four numbers as input for this network, you just have a solution key space from 2 power 4. So you just have to use 16 tries. It's very simple to brute force such a network, and it's sometimes simple for brain. Maybe some of you are thinking it's really working. I've put the solution P0, 1, P1, 0, P2, and P3 set to 1. However, if you try to do this with brain, you will try to start to have some small problems. If you really try to check if every transition is firing or not. However, as well, in this model we have set the lowest priority to T2 because we wanted to prevent any fight between two transitions. And if you look at this net, you try to understand that it might be complicated, to understand such a network. If you remind that you try to analyze code and transform the code to such a network to understand how this thing is working. So this is very easy. We should make it more complicated. And one way is to increase the complexity to decrease the code understanding or the model understanding. And the easiest way is just to copy and paste the network you know which is working 2 times. You can copy and paste it 4 times, 5 times, 6 times. Sounds very easy, but you have to take care that the model, that the feature net is still doing this, what you want to do. You just cannot attach every node to every other node. You have to check if the feature net is still working, if it's still producing the solution. And this is known as a reachability problem. You have to test if it is possible to reach the final transition, T2. If you don't reach it anymore, then you have done something wrong. So this one has some more input places, and therefore we have a more complicated solution. And the solution key space is now increasing to 2 power 16 to over 65 tries. And this is much harder to brute force. And if you try to solve this feature net by brain, well, it looks more complicated. At the first view, I would not be able to solve it within some minutes. Okay, on the left side we have one feature net, on the right side we have the same feature net we have seen one slide before. And if you just look at the right top of the feature net, the smaller part, and compare it to the left one, which one do you think is more complicated? Who thinks the left one is more complicated, more complex? One, not some. The right one? The rest. Well, both nets are equal. they're absolutely equal. You just have moved some places around the slides. You just move some pieces. You just move some arcs, you just move some lines, but it looks absolutely different. So it's very complicated to analyze such things. Okay, you can make units much more complicated. Imagine you try to build up very, very complicated nets to simulate a rail stationary machine. And this would be very, very hard for a cracker just to analyze. But would not stick only to the algorithm or the network. One example, each transition is developed as a thread. Each place is a thread. And you could project each thread different. You could use for each different thread different anti-debugging techniques, and specifically self-encryption, where you could introduce watchdogs, which try to watch each other processes if they are debugged or anything else. So there are many, many possibilities to make this very hard to analyze. One more thing is to encrypt the communication protocols between two places, or the place and the transitions. And one more step would be to encrypt each token. Because a token is kind of an object, you can encrypt it, and you can make it very hard to analyze at least everything. So how would you analyze this? It would take you very, very much time. This is a three-dimensional visualization of such a network. Doesn't matter, but it shows how complicated such networks look if you just visualize them. And now imagine you have a disassembly. You are disassembling the code. Now, maybe you know that there is a KitchenNet in it, and you try to reconstruct the KitchenNet from disassembly and debugging. Well, you need to trace or debug parallel processes. You have to do multi-threading debugging. And it's not very easy, because you have to understand the parallel processes. If you debug one thread, well, the other threads are doing something else. And because you're debugging one thread, you have maybe stopped its state. It's not running. So the KitchenNet is still trying to solve this problem, but it comes to an absolutely different solution. So this is an absolute problem to trace such parallel processes. And if you then have all these ugly protection tricks within each thread, this might be a nightmare. So how would you analyze this? There are some problems of the complexity we have encountered. The problem was that there are many research groups who are doing research on minimizing such KitchenNets to make them simple. There's absolutely no paper, no academic paper about how to make them complex. Because nobody needed it before. And we want to increase complexity. So you might, this might be a good chance to introduce some more research into this field, especially in the protection field, but decreasing complexity is, from the standpoint of math, unworkable. You just can't turn it around. But this is not existing, and nobody has written about it, so if anybody of you want to write about it, you could be the first. But there are no algorithms yet to make it complex, and this brings me to the point that it's very complex to build up such networks. You have to do very much manual work. And this is one point of the discussion. One positive point of such networks, such protection, is that you have a high complexity. You have a very high obscurity. However, it's very hard to reconstruct such a KitchenNet from assembly source code. I will show you later on assembler code, and you can just see nothing. And sometimes it leads into this point that you have protection which is hard or impossible to understand, at least. Well, we have some more points against such protection. If you just once have reconstructed such a network, it's very easy to simplify. There are many algorithms to simplify such networks. It's just a matter of time. And if you once have simplified such a network, you can just run reduced brute-force attacks. So if you are able to reduce the key space from 2 power 16 to 2 power 4, it does not take a second to create such a protection. And once brute force it, it's possible to get a valid key again, or a valid key for the application. The protection is still breakable for sure at the input layer. You can patch it. Okay, we want to talk about this. The next point is that the development of complex filtering nets is very, very time consuming. The example you have seen there took some time. Some more time to test, to check it really works. It was a very, very small example, but we had to do some work in it to test it, it's really working. And so the implementation is very complicated as well, because you have to transform such a network into assembly code, for example. And this might be not very easy, because there are no automatisms for this at the moment. So, what are the results? Filtering nets are a very efficient way to obscure into complex processes, and they're very resistant against brute force. But if you once have analyzed such a network and such a protection, it can be simplified and very easily cracked. We have some example source binary available. The source code is attached to the paper I've submitted, and it's binary with possible papers will be published online, so I can put the binary in there as well, so we can play a little bit with it. So one more negative point about this fact is also the protection schemes have been failed. And if you have such thing, it makes fun to reverse, but it's not a real protection. And if the code is runnable, it can crack it. So therefore, further research should be necessary. And I would like to show some example code. At first, I want to run such a network. Okay, just look at the solving time we need to solve this network. It's quite a huge network. Oh, there's nothing to see. Wait, it's solving. It's solving. It's quite a huge network. Okay, shift invalid key. That's all. Okay, what you have seen here is we have quite much time to solve this problem. I told you that it's a quite huge network. How many nodes do you think does this graph has? 100, 1000? Who thinks 100? Well, 1000 maybe? It took some time. Okay, 7. This just had been 7 nodes. 7 nodes to solve. And that's why this protection is not very the fastest. It's very slow. And we just have 7 input nodes. That's absolutely slow. So, useless. If you look at the disassembly code, we use an online disassembler, and we can just open the file. Well, you can change the style if you want to soft ice, either or debug, whatever you like, and set some disassembly options. And as well, we have in this disassembler PE editor, if you like to see the information. Just to say one more word to this disassembler, it's pure written in PHP. There's no C++ code, no assembly code, it's PHP. It's completely written in PHP. So absolutely safe against anything. And if you try to disassemble this code of the feature that I've shown you before now, and you see not very much. What you see is we have can you see? What you see in this code, if you analyze this protection, well, you see not very much. You see create thread, create thread, create thread, thread, thread. Okay, we have many threads. Then we go to some small code. Finally, we are here. Okay, it's a jump not 0. We are able to patch the file, but that's our intention. And the rest is very, well, not very useless. You have just a small subroutine who's doing something. But if you try to read this code, well, you need some time to understand what it's doing. Because you have all the threads and so on, pushing values to each other and trying to do something. So from pure disassembly code, you're not able to understand what's really doing. Or you need some more time really to analyze it with your brain. Okay, so very fast. Some acknowledgement. One acknowledgement goes to Robert REcon. He comes from the Polytechnical University of Odessa, and he had the initial idea to this. I really have to mention him. And as well, the REcon 2005 team has done a very great job here during the last days. Of course, anonymous reviewers and the audience. And okay, should be the end. Just some advertisement. We are doing at the moment reverse engineering Schnoppix CD, live ISO, just including tools for reverse code engineering. It's an alpha state next to beta state, and just for information, it contains all tools you need for reverse engineering on Linux systems. It's not a hacking CD, it's a cracking CD. So if you want to have a hacking CD, there are several other distributions. Okay, questions? But I would like to have some assistance that I'm sure to understand all questions.
Theory or any theoretical work been done on dual graphs? Because if you look at the usually graph theory, you can switch from arrows or and points, and look at the other way around. Shift the graph, adding the endpoints, being arrows and arrows.
Do you mean if I myself have done some research in REcon such protection and changing the graph layout? No, not yet.
Has this been done at all?
No, not by me. I'm not sure if somebody else has done some things with Pitwin-nets, but no, I'm not aware of it. Maybe.
Can you tell how you communicate, how the transitions work and how you communicate between threads?
The communication between the threads is very easy. You just put some values into registers and read out the values. You can see the source code later after the talk if you like. It's very easy. No more questions? And no? One more?
That's the impact of time consumption of the REcon process against the rate of precision techniques.
I actually didn't hear the full question. I heard, what's the impact on, I heard you say, what's the impact on some process for obfuscation techniques? Could you ask your question again?
I mean, if I want to obfuscate the process with a Pitwin-net, we run faster than Pitwin-net than with regular protections.
Oh, how does the protection offered by the Pitwin-nets compare in terms of speed to other protections? Will it be slower than other known protections, faster?
Well, as we have seen in the example, it's very slow. It's definitely too slow. So I would not recommend to use it really in any protection system, because if you want to make the protection very complex, the solving time increases maybe exponential, and well, no user wants to wait 2 minutes until the software is ready. So, well, maybe you can speed up some things, but that's a problem of such networking, which the big research groups are dealing with. They have very big models to solve. They have very huge machines to calculate such complex networks, and they let run the machine sometimes weeks just to solve a problem. So for software protection, just for shareware or whatever, I would not recommend it. It's too slow.
I didn't exactly get what you were saying about the multi-threading, like debugging, that if you were debugging one thread, like basically, how are the threads like staying in sync with each other? You're saying you're debugging one, the other ones are still running or not really. So how would that work? Just like, how does that still work with just a normal thread span? How are they all?
Can you explain how the threads communicate with each other to make the protection scheme work?
And also just how they stay in sync, and then how does the sync break with debugging?
How do they stay in sync? And how does debugging it, how does synchronization fail? When you're debugging it, will the synchronization fail? Is there any checking in the thread communication that would fail when you're debugging, so that debugging would make it impossible to crack it?
Well, there's no anti-debugging technique at the moment. You could implement it very easily. The main protection part of what I have introduced here is that if you stop one thread to analyze it, the other threads are still running. And they're trying to solve the network. Over the time, you try to debug one other thread. That's one way to protect it, but we might introduce watchdogs or like anti-debugging tricks to prevent such debugging attempts. Sure. Was that your question?
But well, sort of, you said that like you're gonna get a different answer if you're like stopping.
If you stop one thread, or if one of the threads isn't running because you're debugging it, would the outcome of the internet checking be different?
Well, if you think that each place, each node in this graph is a different thread, and you stop one node in running, the rest of the threads are still running and trying to do something, pushing tokens one to each other, but the model is not the same. It's not the same graph. And because you stop one node in the graph, the model is different and you get an absolutely different solution. You might be correct if you start the correct thread. You might solve the problem that's very easy, and you create the protection that you reach the transition, which has to be fired at last, just with a second. So if you maybe stop enough nodes to work, it should be very easy to crack. But you don't understand how the network is working. And that's a goal to reverse engineer the network, how to understand the network, not just to do fast patch, to stop all nodes and just to let the application run with one thread and finally fire transition. So it's more like a puzzle. You want to try to understand the network and not to simply patch it.
How would this work if you're trying to use it for a registration scheme where each user or each machine has different codes? Presumably with this sort of system, this presented at the moment, when one person has bought it and has a solution to the net, doesn't that mean that it's incredibly easy to optimize it for any name or user?
What would stop a person with a legitimate serial from spreading that serial to other users?
Analyzing the network.
And then, sorry, can you repeat that?
Analyzing the solution that he gets from his serial that he's.
And then using that known valid serial to analyze the Petri net to better understand it.
So you're talking about brute forcing the network.
If you have a working solution,
Yeah.
then you modify that to get serials that are useful to people.
Having another solution to make easier for users.
Yeah. There's only one solution for this network. So there's only one input key which should work. For sure you can make some other models which are able to work with several solutions, but this example is with one input key which solves the problem. You can make it more complicated, but the example just deals with just one input, one working serial, that's it.
So it would be more useful for authentication purposes than for persons than for protection from self-respect.
Oh yes, of course. You can try to identify several things like social numbers or whatever with it, but it's not the way to deal with such problems. This is not a model or not a method to work with such problems to authenticate anything. That's too slow for such things, in my opinion.
So then as a serial number scheme, would you do a customized Ethernet for each user that you give an executable to? And does that serve as a watermark as well?
Okay, the question was if we make such a solution, we have to make a new application for each user. Well, sometimes it should be the best to have this one application for one user. It's best to stay, it's kind of watermarking. You can always trace who has done this. Well, since I don't implement to use it really in real life, it's more a concept. It's a game to play with to have some more reverse engineering puzzle. But yes, of course, since there are no automation tools to construct such picture nets for a given number, to reproduce some solutions or whatever, I think it's very complicated to do this.
What's the complexity theory of solving the problem of solving sections in general?
It's not my field to dig into this. It's just a basic example, basic concept, how we might use this. I'm not a specialist in complexity theory or picture. I'm very sorry for this.